So this is August 11th, and this is the Western Automation 7 a.m. Monday morning training class. We have a little schedule change today, and we're going to talk about best practices as it relates to installing VFDs and servo amplifiers. But these best practices can apply to anything you're doing in the instrumentation field, whether it's machine control, process control. These best practices are aimed at preserving signal integrity and suppressing disruptive electrical and electronic noise. And you'll find that nothing here is very expensive. Nothing here is very difficult. It is a matter of consistency and discipline, using the right tools, and just being aware of what it is we're trying to accomplish. So before I get started on the actual presentation, I want to talk a little bit about the types of noise that you see. And there are a lot of videos on this. I did a class recently for the LA County Sanitation District engineering group down at Workman Road. And their concern is valid because they are an instrumentation process control environment. There are a lot of sensors. There's a lot of drives in their environment, whether it's water or wastewater. You know, we're pumping and agitating fluids, but we're also monitoring all the processes. A lot of flow control, a lot of variable frequency drives, a lot of 700-volt DC buses getting chopped up with pulse width modulated signals to the motors. And if you don't keep good practices, that environment becomes extremely noisy and extremely unreliable. So this group was justifiably concerned and wanted to learn what the current, I'm not going to say state of the art, but acceptable best practices are today, using the technology that is available to us. So we're going to start by defining the difference between common mode noise and differential noise. And I may just, I am going to call up one of those videos because they do a much better job of it than I do. Bear with me 1 second. All right, so let's make use of the internet the way we should.
It gets worse after eating a lot of processed foods. Some recent studies show that certain ultra-processed.
And this is a short video, so
noise, the following two terms.
Hope I got one that isn't in some bizarre accent.
Terms often come up: differential mode noise and common mode noise. But what does it actually mean? And what are the differences between the two? Let us perhaps first clarify the question what a differential mode signal is. A differential mode current is exactly what we have been learning since high school.
We had a really nice
current flows
in Atlanta, and the station got sold out from under.
The desired signal is the difference between the two potentials referred to ground. So far, we haven't had any noise. However, In switched mode power supplies, for example, high currents are switched very fast, and the signal may look something like this.
Now, a switched mode power supply, that's a very good definition of a variable frequency driver or a servo amplifier.
Small overshoots contribute nothing to the useful signal, and thus it is called noise. We want to get rid of this noise, and it can lead to a malfunction or interference. Furthermore, regulations exist that set limits for such harmonics. So it is our task to remove this differential mode noise. For this, we can use a simple LC filter. Since we want to keep both lines in balance, we use an inductor in the return path as well and divide the initial value by 2. Because we connect the capacitor across both lines, we call this filtering element X capacitor. But using filters is just one way to mitigate differential mode noise. We could also improve the PCB layer to reduce loop areas, but more on this in a later video. Now let's talk about common mode problems, which are somewhat different and often more difficult to control. You have these especially if you have longer connection lines. Then these act like antennas. Imagine we place a cell phone next to these long connection lines. High frequency interference can then couple into our circuitry. This noise current then flows in common mode and disturbs our DUT, the device. This works because our source and load are located near the chassis. So common mode problems result from parasitic elements in the circuitry. Even if these parasitic capacitances were only 10 picofarads in value, a 1 GHz noise signal would see an impedance of only 16 ohms.
Okay, that's getting a little bit deep for what I wanted to talk about, but you get the idea. Differential mode is between two live conductors. Common mode is between both conductors and the ground plane. So common mode noise, as he accurately stated, is much more difficult to get rid of. Now, in the case of the VFD, differential mode noise, as he illustrated in the, let's call it his, when he was talking about switch mode power supplies, this overshoot here is going to cause a lot of differential noise, and I'll show you ways to suppress that. However, the common mode noise that we're going to deal with today with regards to outputs of VFD amplifiers, servo amplifiers, that is caused when we have between the three phases of the output a voltage. Now that might sound very strange, but let me just dump this for a second. I'm going to go, just because I didn't have a chance to pop this up the way I wanted to, I'm going to show you this. Okay, so this is a three-phase power supply, okay? It's basically 3 single-phase sine waves displaced 120 degrees from each other. Standard stuff. Now, at any point, and this is going to illustrate it a little bit better, at any point in time, oh, I got slow internet. At any point in time on a 3-phase power supply, the total voltage is 0. If the sine waves are perfect and the displacement of 120 degrees is perfect, we always have 0 volts between all 3 phases. If we look at it here, we have a full height and 2 half heights in the negative, 0 volts. Common mode noise occurs when we do not have 0 volts, and therefore we have a common mode voltage. Common mode voltage should be 0 in this case of a perfect three-phase power supply. The VFD output is not 3 sinusoidal phases. Now, let's talk about pulse width modulated DC bus-based VFDs, because this does not apply to Yaskawa's matrix technology. And I'm not going to talk much about matrix technology today. We'll do that in another class. But the Yaskawa matrix technology is sinusoidal on its output. It does have some harmonics, so it has some common mode noise, but it doesn't have anywhere near the common mode noise of a PWM VFD output. And a PWM VFD output, instead of looking like that nice sine wave, is looking like, yeah, this is a good one. So this is just one phase for illustration. This is a sine wave. This is the output of the VFD. And when you have 3 of these PWM patterns, you have a lot of common mode voltage because they don't sync up perfectly. Not just because of the overshoot on every one of these spikes, but because of the nature of the pulse width modulated signal. So we have common mode noise. And that is a short impromptu discussion of differential noise and common mode noise. Now, with regards to best practice on VFDs, we have to consider the entire system. That's the guiding principle. We need to consider the power supply, which is our 3-phase power supply, plus any other low voltage power supplies that we're using, and the VFD and the cables and the motor that we're driving and all of the instrumentation that's in the neighborhood that we need to protect from interference. Now, this componentry doesn't just result in spurious signals that cause trips. It results in equipment damage, and especially the common mode noise on the power output, because there's some power behind it. We'll talk about that in a second. Now, the principle of harmonic distortion is basically you have a desired waveform, and then you have an actual waveform that isn't the same as that desired waveform, and the difference is called the harmonic distortion. We want a sine wave. You saw from that last picture of the PWM output, that's not exactly a sine wave. It does result in a sine wave effectively for the motor torque generation. The motor itself is considered in this circuit an inductive filter to filter that PWM into a sine wave and therefore produce sinusoidal current in the motor windings. But that PWM signal on the way from the transistors in the VFD to the motor causes all kinds of havoc. IEEE 519 is a definition of a standard for harmonic mitigation. And to what point do you want to mitigate these harmonics? And basically it defines things in terms of a percent of distortion versus the fundamental pure waveform that you're after. So if the sine wave is 100%, IEEE 519 in the broadest sense is going to tolerate around 5% distortion. A PWM output unfiltered to a motor, probably 80% distortion. The reflected harmonic distortion from the diode bridge of the VFD back to the power line, based on the way that the diode bridge pulls current, it doesn't pull it sinusoidally, or at least not 60 hertz sinusoidally. Again, 70, 80% distortion. We have to filter this stuff. You can't just let it sit out there in its raw state, causing electric noise havoc. Now, I'll temper that remark by saying that in large systems, let's say you got about 2,000, 2,500 kVA total power, and we're talking about a 5 horsepower drive. In that case, you probably don't need to do anything. That 5 horsepower drive is a small fish in that big pond. But when your non-linear or distortion type loads are close to a third or a half or worse of your total power on your system, you definitely need to start dealing with it. With regards to signaling leads, you always have to deal with it. Okay. We had a class last week that referred to short circuit protection, and I don't need to go into that again, but we do need to protect the VFD when the power supply is not perfect three-phase, 120-degree displaced sine waves. A lot of things can happen on the power grid. The utility company, during heavy load situations, we're in the month of August, so we're experiencing that now, especially in rural areas where the load starts to cause the line voltage to sag. Well, that's, the VFD is not going to like that. The power company is going to try to raise that voltage. And in the case of poor power factor, in this case, the not the distortion power factor, but shoot, I've lost the term. It's leading and lagging power factor, where the current lags too far behind the voltage waveform on the power line. And this happens during heavy load situations, such as everybody running their air conditioners in August. The power company will switch in power factor capacitors to put more of a leading power factor and compensate for the current lagging the voltage due to heavy load. So we have voltage sagging, we have current lagging the voltage waveform. The power company does various things to correct that. And by the way, when they switch in these power factor correction capacitor banks, they're huge banks of capacitors. They do that with contactors. They send a shock down the power line. If you're close to that, it's like being near a lightning strike. The voltages can get pretty severe and have very sharp rise times. So these kind of distortions, we need to protect the VFD from the power line issued distortion. A near lightning strike, well, if it's near enough, you're not going to be able to do anything. But if it's 2 miles away, it's going to send a voltage shock down the line, similar to a power factor correction capacitor switching on. And at that point, you have another voltage spike to deal with. Now, the first thing that I recommend everybody use on incoming power to protect the VFD is the Raycap Strike Zorb or some similar device. You will notice on the Yaskawa products and on most other VFD products that you get these three little colored lollipops, red, green, blue, seen them in black, that are called metal oxide varistors. And a varistor is a resistor that varies its resistance value based on voltage. An MOV is a voltage clipping device. Its resistance goes up when the voltage goes beyond a certain value. And they're nice to have on the input of your VFD to clip off voltage spikes coming into the VFD itself. But they don't have a lot of mass. They're about the size of a nickel or a quarter. And it's mass that absorbs the joules of energy. So if your voltage spike coming down the line is from a power factor correction capacitor bank, let alone a near lightning strike, you need more mass, and that's what the Raycap strike sorb is. You can see those things are like short beer cans, or well, I don't know what else I would compare them to, but they're little round cylinders, maybe 2-3 inches in diameter and 2 inches and 3 inches tall. They're big. They have a lot of mass. They will clip a lot of joules of energy. And as you can see, they're installed on the output of that short circuit protection device ahead of the lines going into the VFD. Now, I'll talk about this in a second. So here we have a voltage clipping device, phase to phase, of some mass to handle pretty strong voltage spikes coming down from the line. Here we have an input line reactor, and that is a big inductor. It resists changes in current. Here we have a voltage spike absorber. Here we have a current shock absorber. These all before the power lines go into the VFD itself. So that's how we protect the VFD when we're in a hostile environment. Now, I've always said the VFD out of the box is like your stereo, and you treat it like your stereo or it's going to fail. When we put drives in hostile environments, we have to take into account the voltage and distortion from the power line that we just spoke about. We also have to take into account temperature, water, dirt, bugs, rats, what have you. And there are devices that we use for best practice installations that account for these threats to the VFD. The first thing we want to do is make sure that our ambient temperature is suitable for the design that we are using for the VFD. In most cases, we're going to be putting the VFD in an enclosure. And that enclosure is going to have to dissipate the Watts loss of the VFD. The VFD will produce probably 2 to 3% of its total rated power output in heat loss. Watts losses, by the way, are published in all of the Yaskawa VFD manuals back in the supplement section, and they're actually published as total Watts loss, and they're published as a percentage of that total Watts loss that goes off the heatsink, which is about 80% as a rule, and then the remaining 20% comes off of the circuit boards and the actual devices that are mounted on top of the heatsink. The reason for that is we do a lot of heatsink out the back designs where we isolate the heatsink thermally from the electronics, and we're able to isolate 80% of the Watts losses into a chimney, if you will. We blow a hurricane across that chimney, and it never affects the components that are in the sealed off electronics section separate from the heatsink channel. So most of our VFDs properly configured can stand 122 degrees entry air into the heatsink. And that phrase is so important because if you put a VFD into 120 degree ambient, like an installation in the Mojave or the Sonoran Desert, and you say, oh, I'm good to go. VFD is rated 50C, which is 122. But you haven't accounted for sun load, which adds more heat. You haven't accounted for radiant heat from other devices, and you haven't accounted for the fact that the heat builds up in the enclosure and you haven't provided a way to evacuate those watts. Therefore, it's not ambient temperature, although we say that, it's air entry temperature into the heatsink. At the bottom of that heatsink, because we always draw the air up, I want 122 degrees or less. In the case of a standard VFD that's rated 40 degrees Celsius, 104 degrees Fahrenheit, I want 104 degrees or less. On the opposite side, I want a space heater. Why? Because if you think things don't condense in the desert, I don't know if you've ever been camping, but I've woken up in the desert inside my tent, and there's water on the inside of the tent. Why is that? Well, it's because there is some humidity in the desert. It's not zero. And if the temperature drops low enough, the dew point will be reached. And below the dew point, you get condensation. You do not want condensation in a VFD cabinet. Therefore, you put a space heater in there, preferably one of the modern space heaters with a dew point sensor that will turn the space heater on to prevent the inside of the cabinet from ever reaching below the dew point, and therefore preventing condensation in the panel. Because we have to evacuate watts in the panel, we need filters in many of the cases. I can't tell you how many times in a month somebody says, oh, I want a VFD in an NEMA 4 cabinet. And notwithstanding smaller horsepowers where we can get some washed down VFDs, and these have exposed heat sinks, and the heat sinks are probably 2 or 3 times the normal heat sink for that low horsepower drive. I'm talking maybe 1 to 5 horsepower, maybe 1 to 10 if you're really stretching it. These can cool ambiently. Try putting a 100 horsepower drive in a NEMA 4 can with no ventilation. You'll get an anticipated result within a very short period of time, and that result will not be to your liking. We have to run air through these enclosures. Can we air condition? Yes, we can. The air conditioner adds another failure device. It's actually a single point failure device. Now your air conditioner has to be suitable for all this hostile environment. And it consumes more energy. In sum total, if you can get away without an air conditioner, that is clearly the choice. One thing Yaskawa has proven to the VFD marketplace, and many of those applications initially took place out here in the Central Valley and the Mojave Desert. I was involved personally in them. We wanted to eliminate air conditioners on outside duty applications. We succeeded. Yaskawa has a product all the way up through 1,000 amps that can be installed out on a cement pad, no shade, in full sun, and cool itself without air conditioning. And we've got them all up and down the Central Valley, in the agricultural world, in the Mojave Desert, out in Arizona. These are the worst possible places for this. And they do just fine. Thank you very much. We're now pushing that philosophy into the water wastewater market, and it's been accepted. That's one of the most conservative markets you can get into. We don't need no stinking air conditioners anymore. But we do need airflow. And if we have airflow, we have air filters. And one of the keys for best practice is to make the air filters easy to change out so that people change them out. If you make them difficult, they're not going to change them out. If you got to suit up in an arc flash suit to go open the enclosure door to change your air filters, it isn't going to happen. So you want the air filters to be designed such that they are accessible from the outside of the enclosure without suiting up in an arc flash suit to open up the door and expose yourself to all that high voltage. And we want to make it easy. Sometimes we can even make them washable, but in many cases, with the fine silt that we deal with in agricultural situations, we need a better filter, and that filter needs to be replaced pretty much on a 2-3 month basis. And then we need to seal all of our wire conduit entries. Again, we're talking about protecting the VFD here. I've seen applications where I've got a 3-inch conduit and code says you're supposed to have about a 60% fill in that conduit. That's enough for a rat to climb all the way through that thing like some tunnel engineer in a German POW escape movie and he comes into the cabinet and starts chewing everything up. And you open up the cabinet, and there's that poor critter blown apart because he touched two conductors, and the stench is awful, and you got to clean it out. Not only that, you probably blew something up. So seal the wire conduits. By the way, I think pincher bugs personally can pass through brick walls. I don't know how they do it, but I don't think I've ever opened up a cabinet in Southern California that didn't have a pincher bug in it. Okay. Proper grounding, a huge portion of best practices. Drive a ground rod, but grounding is more complicated than just that. Driving a ground rod and connecting it to a copper bus bar in your cabinet, that's all fine and dandy, but how you ground all your components to that copper bus bar, we're going to be talking a lot about that. Now, let's talk about the concept of the Faraday cage. Oops, sorry. The Faraday cage, Faraday was a scientist, and he discovered that when you have a cage that is grounded, a conductive cage that's grounded, the charge inside the cage is zero, no matter what voltage you put on the outside of it. And the picture on the right is not something that you really want to try, but if that cart was properly grounded, and notice that it's not, it's because it's on phenolic wheels, so that guy in the cart is dead. If it was grounded, it would be a Faraday cage. Now, you take that Faraday cage and you apply it in different form factors, such as a tube of shielding around your conductors, properly grounded. You have a Faraday cage around the conductors inside, protecting not only the conductors from external noise coming in, but if there's noise on those conductors, it protects it from emitting out. The shield is like an electrical condom. As long as you don't have a hole in your condom, then you're good to go. This is what shielding looks like on cables from a practical standpoint. These happen to be control cables, so we're protecting the signals inside the cables from external noise, such as the PWM 700 volt spiking to 1500 volt output of the VFD. Note, the highest quality stuff has got a braided shield and a foil shield. By the way, this is the drain line. This is not how you ground the shield. Foil, braid, foil, braid. This is a cheap conductor. It just has foil. What is this cable lacking? The ability to sync high frequency noise to ground, because its shield has a certain amount of surface area that is less than this braided shield. When you have both, the low frequency noise tends to travel on the foil shield. The high frequency noise tends to travel on the braided shield. Look up Litz effect, L-I-T-Z. Well, just look it up. I don't have time to go into it. But basically, the more surface area you have, the higher the frequencies you can carry without a lot of impedance. And there's a lot of surface area on a braided shield because you have all these little wires making up the braid. Therefore, because high frequency noise tends to travel on the surface of a conductor, high frequency signals in general will tend to travel on the surface of the conductor. You have more surface area here, less impedance, better path to ground for high frequency noise on braided shields. Now, maintain the integrity of the shield along the entire cable, no holes in the condom. Do not splice. run the whole conductor. If you have to splice, that is a potential hole in the condom, and it's leaking, and you're leaking noise. Oh, by the way, I want to go back to this for a second. You see these little twisted cables here? That's the third level of defense for signal integrity. You twist the two cables around each other so that you cancel out differential noise, not common mode noise, differential noise. Then you put it in a foil shield, then you put it in a braided shield, and now you've got pretty much the best possible protection for your signals if you ground the shield correctly, which we'll talk about in a second. And yeah, okay, let me go there. The third bullet point is what everybody does in this country. When I was not actually trained on this kind of thing to U.S. standards, I had the luxury of being trained by the Japanese. And when I saw the way we twist a shield up, put a little bit of heat shrink on it, put a stake on or some sort of ring terminal on it and put it on the ground lead and think that we've done a nice, neat job, I looked at it and said, no, you just created an inductor. You've increased the impedance path from that beautifully designed shield around the cable to the ground point by twisting the shield up. When you increase the impedance, you trap high-frequency noise on the shield. And it doesn't have any place to go. And then you start creating capacitive discharge as a result. We'll talk about that in a second. When you intersect cables like a power cable and a control cable, you intersect them at 90 degrees to minimize crosstalk. You always separate your control and your power leads to the maximum extent that you can. When you design your VFD cabinet, you bring your power in on one side and you run up the panduit and cross over to the points where you have to land your power conductors. You bring your control in on the other side and you minimize any proximity between your control and your power. If you don't do this, then you're going to have a lot more crosstalk. So shielding and separation is the rule here. Separate power from control, shield everything, and properly ground it, which again we'll talk about in a second. When you want your enclosure to be a Faraday cage so that the VFD inside doesn't become the local AM station broadcasting out to everything in the plant. A very important point is to use a braided strap between the door and the enclosure body itself. That steel enclosure is a relatively good Faraday cage, but the connection between the door and the enclosure, especially if it's a NEMA 12 or NEMA 3R or NEMA 4 enclosure, don't use NEMA 4 enclosures with VFDs, the rubber sealing gasket can tend to cause isolation of the door from the body of the enclosure. The body of the enclosure is grounded, therefore the door will not be. Use a braided ground strap to ground the enclosure door to the body of the enclosure and therefore to the ground plane itself. All right. Now, here is how you ground a shielded cable. Here is how you do not ground a shielded cable. Taking the drain wire and the shield, twisting it up around itself and landing it on some ground point. Note, T1, T2, T3. These are the motor leads. These are the big noise producers in the VFD. This shielded cable is designed nicely up until here. Then the critical components of this happens to be a pressure sensor coming in. So it's a maybe 0 to 10 or 4 to 20 milliamp signal. I have exposed conductors in the direct proximity of the power transistors and the lines going to the motor. And this shield creates a high impedance path from the actual shield to the ground point. Bad on several counts. Very commonly practiced. This is how you ground a shield. You take a tool that looks like this. This is a little blade. This little blade rotates 90 degrees in that, and this is how you do it. You first cut. You can adjust the mini blade in there, and you first cut a circumferential cut about 1 inch apart. And then you use the blade at 90 degrees to cut this incision, and then you pull the jacket off, exposing the shield. If you set your depth correctly, you will not have cut the shield. You can also do the fancy method of, on bigger cables, this is actually the way you want to do it. This is too difficult to do. But either way, as long as you get that jacket off, and that jacket can be PVC or whatever you want it to be, I don't care. We'll talk more about the actual jacket around the conductors. And in this case, we are a conductor, so this could not be PVC. It has to be cross-linked polyethylene. But we'll talk about that in a second. Now you've exposed your shield, and you can put it into a proper ground clamp. There's a surface area there and a pressure. There's a whole cottage industry in Europe that builds this stuff. You mount it to your DIN rail. Now you've got and the DIN rail, of course, is mounted to the ground plane inside the enclosure, which is mounted to the ground rod that's in the earth. There are different form factors of these clamps. They're not expensive. The amount of labor that you'll save doing this, not to mention the fact that you're going to do a good job in suppressing the noise. So there's so many different ways or so many different reasons to justify this method. You must do this when you ground a shield. Note, you have not disturbed the manufacturer's very carefully designed foil and braided shield structure with its rated impedance as a result. Disturb the shield, change the impedance. You won't be changing it in the positive direction. Now, with all that said, there's something else. Look, I've got shield continuing on past the ground point. So if this is where I enter the cabinet with signal leads coming from the external world, and at the first DIN rail at the bottom of the cabinet, I shield the cable, I can now carry the shield all the way up to where I landed on the component somewhere up in the enclosure subplate. I don't have to do this. In fact, here's kind of a cool thing. This little device, that's a one-time braid clamp and a grounding post that's connected to the ground plane. What's done here, and I would have extended the shield even up further, is you ground it right at the VFD. It's kind of cute. Again, not so much cost. You understand the point. Keep your shield integrity, you maintain your shield integrity all the way as close to the landing point of those sensitive signal leads as you can. Okay. Now, other methods to terminate a shield properly. When you want to put, for example, a connector on the end of your shielded cable, I highly recommend that. Connectorized cables are a lovely thing. They don't pass through small holes very well, but there are some products that are made by a company called Isotek, I-C-O-T-E-K, that allow you to pass the camel through the eye of the needle easily. In other words, connectorized cables through the enclosure wall. Check them out. There's another company called MUUR. There's several others. I believe Lutze Cable Company has these kind of fittings. Basically, what they are cable glands. You cut a rectangle in there, put a frame in it, and you have these compressible cable glands, and you put the cable gland around your cable. The connector passes through the big rectangle, and then you slot that cable gland into the frame and compress it, and you have an IP67 protected ingress point into your enclosure. Nevertheless, you fold the shields back. You don't twist them off, but this is, let me juice that up a little bit there. That's what we want. That's another way of doing it. Instead of your cable clamps, but here, oops, that's always hard to navigate. This is what I was trying to show you right here. You basically folded it back, your conductors are exposed, and now you can go ahead and mount your chase nipple or your connector and still have a proper integrity to the shield itself. When shielding and separation fails to mitigate the problem, only then do we go to filters. Don't go to filters first. First, they add cost. They add heat to the enclosure. And if you don't need them, you don't want them. But there are all sorts of filtering mechanisms that can be used if shielding and separation do not work. Again, filtering is a last resort. Different types of filters for control leads. The old ferrite bead. Carry a bunch of them in my toolkit. These split in half, and you can literally clamp them around the cable. In this case, why the loop? The more times you pass through the ferrite bead, the stronger the noise suppression. Here is a ferrite bead around 3 phases. This is UVW, which is European for T1, T2, T3. So these are motor leads. This is a common mode noise filter. Note all 3 phases are passing through this filter. Remember, all 3 phases at any time should have relative voltage 0. If they do not, this is one way to suppress common mode noise. Here, again, is a conductor wound around a magnet ring. The more times you wind it around the magnet, the more impedance you create. By the way, all these reactors and whatnot, these big magnetic copper filters, they're nothing more than copper wound around iron also. Magnetic grade steel, so it's an iron alloy. And you take copper and you wind it around it, and you get an inductor. Principle used here. We don't need to read this, but you can, it'll be in the presentation that I emailed to you later on today, along with the schedule that I promised Steve to send out. Steel conduit is not a shield. Don't use it as a shield. If you do, it's like jumping out of a plane with a holy parachute. And I don't mean a religiously holy parachute. This doesn't work. Pipe benders bend pipe to carry conduit around without any intention of maintaining the ground path. So you get all kinds of bends and breaks in the conduit that they connect with connectors. And is this a known impedance path? Absolutely not. Nor should you expect it to be. I need a known impedance path to have a proper shield. to carry noise to ground, whether it's on power conductors or control conductors. Steel conduit is not a shield. Now let's talk about power conductors, because the best way to suppress noise is to suppress it at the source. So if you're suppressing the noise production power conductors, T1, T2, T3, or UVW coming out of a VFD to the motor, then you're more than halfway to solving the problem. If you are going to take this path, you're going to need to use VFD duty cable. We've got a presentation specifically on VFD duty cable coming up, so I'm not going to belabor the point here other than to introduce you to the fact that, look, braided and foil shields, high quality. And around all three conductors, what is this? That's what I normally see. 4 conductors, because I need a ground. This design is optimal. We do use a lot of this, but this design is optimal because I've got my 3 power conductors geometrically opposed to each other, so there's some cancellation of noise there. I've got my ground conductors nested in there. I have a smaller diameter cable that's more flexible. Note that this illustration also designates highly stranded cable, another characteristic of VFD cable. Litz effect, again, look up Litz effect. It carries the high frequency noise, like the 15 kilohertz switching of the PWM VFD or some servo amplifiers that are switching north of 20 kilohertz. That's high frequency. It carries it very nicely because there's a lot of surface area there. Now, one other thing I'm going to, oh, by the way, this is a great link to learn more about it. There's several other characteristics that I'll mention briefly here. This conductor insulation here, not the jacket. Jacket can be PVC. This has to be a cross-linked polyethylene, XLPE. That is de rigueur for VFD cable. Why? It allows the cable to have a lower capacitance. And a lower capacitance, well, go to driveflex.com or attend the session on VFD cable and you'll find out why low capacitance is very important in a VFD cable. So this is power VFD cable. Now, we'll finish quickly. I am going to run over about 5 minutes. So here is basically a block diagram of how noise works and how shields prevent noise. If this is your shield, and this is your VFD cable going from the VFD to the motor, the noise coming off of it can't pass the shield if the shield is properly grounded. Right? Common line, grounded. There's your sensor signal. This shield has to be 100% no leakage. What is the damage that I referred to from common mode noise? And by the way, as at the end of this, right now I'm going to talk about how to ground power cable. Motor lead cable, VFD cable used for motor leads. You ever had that discussion? Well, I ground at the source. No, I ground at the destination. I don't give a fine where you ground it, as long as you ground it properly. That whole source and destination discussion is a whole bunch of bollocks. It has no technical merit. I'm saying that on a recorded line. Remember, I said I want you to ground stuff properly, and I don't care if it's in the middle of the cable. I tend to ground all signal leads on one side, and I'll typically do it in the VFD cabinet because it's easy to do there, because I can use all this kind of stuff, but not because it's better to do it one place or another. As long as the shield has a good low impedance path to ground, it doesn't matter where it's grounded. You want to ground it in multiple points? You kind of want to avoid that because that's more labor. Are you going to create a bunch of ground loops? Maybe, but probably not if you're doing this, because your integrity of the impedance path is maintained. However, when we get down to motor leads, using this kind of stuff, I'm going to tell you, you ground at both ends. And you better ground at both ends. Not only is this shield here for the VFD noise to be contained, but on standard VFDs, matrix drive being accepted, we're creating a lot of common mode noise, as we referred to earlier in the presentation. That common mode noise travels out from the transistors on the motor cable to the motor. I want to ground that common mode noise, but I don't want to ground it out at the motor, because then it's going to go into the building ground and travel everywhere. It's common mode noise. What I want to do is I want to use my VFD cable, and I want to use the manufacturer's specified couplings on either end of the cable. And I want to connect the motor side to the motor frame. And then it can be connected to ground, I don't care. And then I want to connect it to the ground at the enclosure cabinet. What I've done is I've created a low impedance path back from the motor to the ground point on the VFD cabinet. Remember, we're generating this common mode voltage from the transistor firing at the VFD. Travels out to the motor. I give it a nice path coming back on the VFD cable shield because I've used the proper couplings, low impedance. And that noise is going to travel back and complete the circuit and go to ground at the VFD. If I have a lower impedance path, it's going to go into the building ground and travel everywhere. And now you got common mode noise on your building ground. And you don't want that. It's going to seek back to whatever place it can find earth. But if your enclosure has a good ground, that's where I want the common mode noise to complete its circuit. Therefore, it doesn't go through the building ground and affect every sensor in Hell's Half Acre. Please ground VFD cable at both ends using the manufacturer's connections, the couplings, and the techniques specified by the manufacturer, like folding the shield back over the outer diameter of the cable and then attaching your connector, and you will have minimized common mode noise. What does common mode noise do? Well, common mode voltage, when given a path of current, voltage times current is power. And it does things like burn out the first turn in your motor winding. It does things like flute your bearings. Why? Because you've got power, right? You got some power here. And common mode noise, if not given a good path back to the ground at the VFD cabinet, is going to induce onto the rotor of the motor. Now you got a voltage on the rotor, and if you measured this voltage, and I have, it runs, 40, 50 volts, whatever, and you think, oh, that's not any big deal. Oh, yeah, it's a huge deal, because every once in a while it goes to zero. And if you're using a good scope, you can see that. And you think, well, why is that going to zero? Well, it's because it's found a ground path. And that ground path is through the bearings. And when it goes through the bearings, the gap between the bearing and the bearing race creates an arc, principle of arc welding. And you start to pit the balls, and you start to pit the races, and eventually you get what we in the country call washboard. Because one divot in the road, you run over it with a tire, the tire bounces, and it creates its washboard. This is washboard on a bearing race, and that's a failed bearing. And you can fail a bearing in 1 to 2 years doing this. Death by 1,000 voltage pinpricks. So the damage is real. And therefore VFD cable, properly grounded at both ends, providing a path back for the common mode noise, is a real solution. All right. Thank you very much. I will email this presentation out. Thank you for staying with me the extra 4 or 5 minutes. It is now 8:04. It's time to go to work. Apologize for the schedule change. We will rectify that in the future. And thanks for coming with us on the journey today. We will see you next week. Have a great week.